Good day and welcome back for the third part of our discussion on trig substitutions. So recall, trig substitutions are a technique of integration. We would usually want to try a trig substitution when our previous methods, specifically integration by parts and or substitution, fails to help us evaluate the integral. Also, in order to apply the trig substitution, we are looking for an expression of a certain form somewhere in our integrand. For example, the x squared plus 1 or the 9 minus x squared. Based upon the expression, there will be a trig substitution that we will want to use and a resulting trig identity to help us simplify the integrand. And we've included those in kind of a tabular form in the previous two videos. And these are most definitely things that you need to be familiar with and able to apply. So hopefully you're keeping kind of a one-page overview going of important formulas and properties. I would certainly throw those trig substitutions on there as well. In this video, we are going to explore two more very standard examples of using trig substitutions. If I was to encounter this first integral, it's not in a form where a substitution can be applied directly, and it doesn't look like integration by parts would be helpful. It certainly doesn't fit any of those standard forms that we encountered. But the x squared plus 1 being raised to the power 3/2 in the denominator is really prompting for us a trig substitution. In this case, 1 is 1 squared, the a value. So we're going to try x equals tangent of theta. This makes dx secant squared theta d theta. So substituting in, we have 1 over the square root of tangent squared plus 1 raised to the 3/2 multiplied by dx, which is secant squared theta d theta. So note, as is the case with any substitution, we're going from all one variable, in this case x, to all theta. There's no middle ground involved here. Once we've made the trig substitution, we simplify. In this case, tangent squared theta plus 1 is secant squared theta. So our integral is secant squared theta divided by secant squared theta raised to the 3/2 power. Note, the square and the 1/2 power cancel. And from a simplification perspective, we have secant squared over secant cubed, which simplifies down to simply being 1 over secant. And in order to integrate this, recall secant is 1 over cosine, which means 1 over secant is simply cosine. And very quickly, this has turned into a quite reasonable integral. Antiderivative of cosine is sine. And our final step with a trig substitution is rewriting in terms of x. And we usually do that by drawing an associated right triangle. So if x is equal to tangent of theta, tangent is opposite over adjacent, so the hypotenuse in this case would be the square root of x squared plus 1. So sine of theta is going to be opposite over hypotenuse. And that completes our example. Note the key steps exactly as they have been previously. Based upon this x squared plus 1, we apply a trig substitution. So put everything solely in terms of theta. We simplify using a Pythagorean identity. And then what remains is going to be a trigonometric integral. In this case, it's about as good as we could possibly expect, it's simply an antiderivative of cosine. The final step is to draw a right triangle and resubstitute. So with that overview in mind, we have a second example, another very standard trig substitution. I would like you to complete this. So pause the video, give yourselves 5 or 6 minutes, and see if we can evaluate this integral. So hopefully you've paused the video, you've invested some time into solving. And I'm going to go ahead and note that I think we could solve this in multiple ways. You could do a standard substitution, and I think get this to work out quite efficiently. But since we are talking about trig substitutions, I'm going to take that approach. So because of this 9 minus x squared, the trig substitution that's going to be prompted is we have an a value of 3, so we're going to use x equals 3 sine of theta, which makes dx 3 cosine theta d theta. So rewriting our integrand, we'll have x cubed. So when x gets cubed, there's a 3 cubed, so 27 sine cubed theta. Then we have the square root of 9 minus x squared, which is 9 sine squared theta. And finally, the dx is going to become 3 cosine theta d theta. And as I claimed before, typically when we substitute in, it's going to look messy. But ideally, we're going to get quite a few simplifications to occur. Focusing in underneath this square root, note we have 9 times 1 minus sine squared theta, which is really why we made this substitution. 1 minus sine squared is cosine squared. So rewriting this, we have 27 sine cubed theta, the square root of 9 cosine squared theta, 3 cosine theta. And note, we can also continue on simplifying this middle term involving the square root as well. So let's take this one step further. 27 sine cubed theta times 3 cosine theta times 3 cosine theta. Whew. So we have 3 times 3 is 9. 9 times 27 is going to be 243. And we're integrating sine cubed times cosine squared. And this is a very familiar trigonometric integral involving powers of sine and cosine. In fact, the power of sine is odd, so this is an ideal scenario. And we can evaluate this using what we previously referred to as the power reduction technique. And this would be in our previous section, 7.2. And I'm going to leave the details to you because I'm guessing you've already solved through. And what you will end up with is 243 over 5 cosine to the 5th power theta minus 243 over 3 cosine cubed theta plus c. And the final step, once we get it to this, involves resubstituting. So if x is 3 sine theta, x over 3 is sine of theta. So drawing our associated right triangle, sine of theta is x over 3. And finally, using the Pythagorean theorem, the bottom leg would have length square root 9 minus x squared. And note, once again, this square root 9 minus x squared was the term that prompted this trig substitution. Cosine theta is going to be that square root of 9 minus x squared over 3. So we need to substitute that in for both of the remaining cosines. So we would have 243 over 5 cosine theta to the 5th power. minus 243 over 3, and we would have that cosine 9 minus x squared over 3 raised to the third power plus c. This completes our current example, and if we've been meeting in person, face-to-face, this is where we would be finishing up kind of our first day of class. So you are in an ideal situation to go to the suggested problems, and I highly encourage you to do so. As you work through these suggested problems, don't hesitate to contact me with questions. So stay tuned and take care.